let's look at first, what does it mean to be uniformly continuous? So this is that kind of review of 131A a little bit, except more generally. We have a metric space K as a domain here. You could make the target a metric space Y if you want. Nothing changes here, but most of the time you want to apply this for R anyway, so I'll try to mostly write statements for target R. Okay, but continuity, we've seen this definition, means that, and the question that you should think is, what is the difference between these two? For every x naught, for every epsilon, there exists a delta that if you're close enough to x naught, then the function values are close. Now, uniform continuity is for every epsilon, there exists a delta such that no matter the pair of points, if they are close, the function values are close. So these two are different. They look very similar. For every epsilon, there exists a delta, but there is a subtle difference here. There are two differences, actually, to be precise. The first difference is here that this choice, because the existential quantifier comes after the for every quantifiers, this delta can depend on x naught, the point you're centered at. Whereas this delta here cannot depend on x or y. This is the main difference that you should internalize, but another smaller difference exists, and it is the fact that here you have a center point and you have another point that's close to x. So somehow there's one of these points is fixed while the other one is moving close by to it. In the uniform continuity, you don't have the center point. Both x and y, they play a completely symmetric role. So this second condition is actually symmetric. And that's a powerful thing to use, whereas the first condition is not symmetric. So that two differences, the symmetry and when is delta fixed and what can it depend on. So just to remind you of 131A things, some examples of uniformly continuous functions: square root of x on the right half plane. Essentially, the derivative remains bounded. So the main thing to worry about is at 0, but at 0, everything is close to 0. So that means that you don't have real issues with continuity. If you have x squared, but restricted to a bounded interval, like -1, 1, then it's uniformly continuous. Again, you could apply mean value theorem to get that. As a function on all of R, f of x equals x. You can use the same delta no matter where you are on this graph. So if you want to restrict the values with an epsilon, you'll use delta equals epsilon. Whereas, and then finally, to give one example in a general metric space, we'll show this in a second, distance functions. Distance functions to a point, those are always uniformly continuous. Now, some things that are not uniformly continuous, the simplest case how to fail is if you grow too rapidly. So x squared on all of R is because if you're far away, the derivative is very big, and delta needs to be small, very small compared to epsilon. And similarly, if you have e to the x squared, it's growing very quickly. On the right-hand side. Of course, if you restrict this function to a bounded, or in other words, compact part, there is no problem. So usually the problem occurs at infinity. So that's one intuition to keep in mind. Okay, so one of these conditions is also stronger. This goes back to on the exam, there was this question about what is the relationship between these concepts. we have two definitions. I mean, let's talk whether one implies the other and whether you can go the other way in some cases. So f is uniformly continuous, then f is continuous. So this is always true for any metric space. And it's quite obvious because here delta can depend on the point. This is stronger because delta cannot depend. So the proof is you use the same delta that the uniform continuity gives you. Okay, but let's see how to prove that something is uniformly continuous. So we have the distance function to some fixed point x naught and on some metric space x, and we want to show that this is uniformly continuous on x. Let's fix an epsilon. We have to find a delta that works for all epsilon, and just like in your last homework, it has to be found from an estimate. So we want to show something for every x, y, in x. We want to look at distance. We want to estimate f of x minus f of y and guarantee that this is less than or equal to epsilon. Well, what is this? This is distance from x to x naught minus distance y to y naught. Now, there's a general reverse triangle inequality that tells you that this absolute value is always less than the distance between x and y. So, lemma, I've stated this before, and if you haven't seen it, then think about how to prove it using the standard triangle inequality. If you have any 3 points, x, y, and z, then if you take distance from x to z minus the distance from y to z, this absolute value is always less than or equal to distance from x to y. And the idea is that you prove it without the absolute values and you move one terms on the other side. And then you prove it with the sign flipped. You flip these terms and then you get the same upper bound. But okay, we have this lemma. This is bounded from above by that. But this is good because we get to make the assumption that the points are close. So if we get to say that the points are within delta, which is equal to epsilon, then we're good. So let's choose delta equals epsilon. Then if distance xy is less than, well, let's write it more properly. So for any xy in x, if distance xy is less than or equal to delta, then indeed we get that. The results are within epsilon distance. So such a function, by the way, has a special name. It's sometimes called one Lipschitz. But we don't need to talk about that now. Okay. Now, another big theorem about uniform continuity is that if you are normally, continuity does not imply uniform continuity. Example would be x squared. I mean, this is continuous, but not uniformly continuous. But if you combine it with this another assumption, xk is compact, then you do get that you are uniformly continuous. So if we have time, I will discuss this proof, but for now, I won't. So this gives you a sense of one way in which what the word uniform means. It means a delta that works for all x simultaneously.